Welcome to Lesson 8, Estimating Means. So here we're going to talk about how to estimate a mean from quantitative data, and we'll be looking at both point estimates and interval estimates. So first of all, a point estimate is a single value. So the point estimate for the mean is the sample mean called x bar. It is the same thing as the average that we're used to talking about every day, which is sum of all of the data values divided by the number of data values. Now the point estimate is a single value, but we really don't know how good it is. So to answer the question, how good is this point estimate, we can compute an interval estimate, which consists of a range of values, and the range of values are delineated by a left endpoint and a right endpoint. Now this answers the question, how good is our point estimate, because we construct this interval estimate based on a confidence level. So that confidence level would tell us how good, and because we use a confidence level to compute this interval estimate is often called a confidence interval. Now, the confidence interval is constructed by taking the sample mean x bar and adding and subtracting the margin of error. The margin of error is directly related to the confidence level. So to get the left endpoint, we take the sample mean x bar and subtract the margin of error. And to get the right endpoint, we take the sample mean x bar and add the margin of error. So let's talk about the easiest way to get the sample mean x bar and the margin of error e. We're going to use Excel and find summary statistics using Excel. Recall that in Excel, to find the summary statistics, you will go to the Data tab, which is here on the top. You will select the Data Analysis Add-in tool. Right here, Analysis. This is the Data Analysis Add-in tool. And when you get to the tool, you will select the Descriptive Statistics Analysis tool. Once you have that Descriptive Statistics Analysis tool, you need to remember to check boxes for output that includes summary statistics and output for the confidence level for the mean. So here we go, Data, Data Analysis. Here is our Data Analysis pop-up menu with our analysis tools. Here's the Descriptive Statistics Analysis tool. When you click OK, there's a spot for your input. The output place, you can choose where you want your output. And down here, you need to check the box for summary statistics. You need to check the box for confidence level for mean. And 95% is the most common confidence level that is used, so we're just going to always stick to using 95%. Once you've done all that, you would click OK, and we'll see how to use this in a moment. Now, the important output in the summary statistics includes, of course, the mean, the sample mean x bar, and the sample mean will be usually the first thing or one of the first things you see in your output. Now, also included in the output are the standard deviation, which is the sample standard deviation that we usually denote as S when we write it out. The sample size in the summary statistics output is called count, and that we usually denote with a lowercase n. So the sample size is called count. We denote it with an n. And the standard error here, standard error, SE, is also included in the output. Standard error is actually found by taking the standard deviation and dividing it by the square root of the sample size n. So the standard error here, which is standard deviation divided by the square root of n, can be computed by taking the standard deviation output and dividing by the square root of the count output. But Excel will do that for you. Now there will also be a output marked confidence level or confidence interval, which I abbreviate CI. And this confidence interval is actually the margin of error that was discussed that's needed to be used to find the interval estimate by adding and subtracting it, or I should say subtracting and adding it to x bar to get the interval estimate or confidence interval. So the output marked confidence interval is actually the margin of error. This margin of error depends upon the chosen confidence level. We're going to usually use 95%. That's the most common. And the margin of error, though, is actually computed by multiplying something called a T-score with the standard error. The T-score is actually not part of the output. We will be discussing what it is and where it comes from. Now, when we actually find our T-score, we actually have to use one of the Excel formulas, T inverse, which is in Excel 2007, or we can use T inverse 2T in Excel 2010. Both of these inputs, or these formulas, require something called the degrees of freedom. And when we are working with estimating means, the degrees of freedom is always one less than the sample size. When finding the T-score, the inputs are degrees of freedom and it requests a probability. And the probability is actually going to be 1 minus the confidence level. So that means for a confidence level of 95%, the probability is 1 minus the 0.95. So what you actually enter into the T inverse formula would be 0.05. And we will talk about that later when we do an example. Let's quickly then run through one of these problems so we can see how this works with actual data. So here in exercise 1 or example 1, we have the weights in grams of 10 Canadian pennies. What we want to first do is find the point estimates of the mean and the standard deviation. Then we're going to find the margin of error and use that margin of error to find the confidence interval and interpret the confidence interval. Then we can actually use that to answer a question or assertion about the weights of pennies. And we can even discuss some sample size questions later on, but it's these first parts here, A, B, C, D, E, that we're most interested in here when it comes to estimating the mean. So notice point estimates for the mean and standard deviation. These are found using Excel and summary statistics. So let's go through that. I already clicked on the Data tab. Here's my analysis tool. So I'll click on the Analysis tool, and I want Descriptive Statistics. So we click OK. And for the input, I'm going to highlight all my data here. Now notice I actually also highlighted the label here so my output will be labeled. So down here I need to check this box, labels in first row, to indicate that the first entry is actually a label, not a data value. I am going to go ahead and put my output in a new worksheet, and I'm going to just label it Sum Stats 1 since it's for our first problem. I need to check Summary Stats, so the output will include all the summary statistics, including the sample mean and sample standard deviation. I'm also going to click Confidence Level for Mean because that will actually give me the margin of error, and I want a 95% confidence interval, so if I enter the confidence level 95%, it'll give me the margin of error for a 95% confidence interval. So now we click OK. And so here now in our output on a new tab, Sum Stats 1, we have our weight. So there's the title, weights. And here we see in the first row, we are given the sample mean. So first output. Notice in the second row, we have the standard error. Okay. Here's the standard deviation. Here is the count. On down here, notice labeled as confidence level, this here is actually the margin of error. Okay, E. Alright, and here is our sample mean X bar. Recall that I mentioned that the standard error here, the standard error is actually found or can be computed by taking the standard deviation and dividing it by the square root of n. Right? So let's go ahead and do that to see how that works. So equals, if I take the standard deviation here and I divide that by the square root of the sample size or count n here, note I get 0.1151, which is the output right here, 1151. So that's the standard error. Okay. Now here is the margin of error right here. This margin of error is going to be used to find the confidence interval. So let's just go ahead and go straight to that. So to find the confidence level, we want our left endpoint, which is found by simply taking our sample mean x bar and subtracting this margin of error, and the right endpoint, which is found by taking the sample mean x bar and adding the margin of error. Okay, so here we are. So here then are the endpoints for a confidence level. Now, remember that our original data here, exercise 1, is to 4 decimal places. So then we will round things off to 5 decimal places. 1, 2, 3, 4, 5, 6. So let's just take one of these away. So we always give our sample statistics and confidence intervals to 1 decimal place more than the original data. So we see here then that our mean is 2.92802. So let's just copy this. Copy. And so for exercise 1, the point estimate for the mean, x bar. Oop, let me go back and copy it. Edit. Copy. Exercise 1. Okay, is 2.92802. And our sample standard deviation S. Let's go get that from our summary statistics. That standard deviation is actually this value here. So I'm going to copy that. Okay, so that's the standard deviation. All right, so there they are, the mean and the standard deviation. Now, the margin of error, remember, was given to us in our summary statistics output. That's this value here. So let's get rid of that. Oops. Okay, so I want to copy this. So copy, go to exercise 1, and so here's our margin of error. Okay, so that's our margin of error E. And then the 95% confidence interval, all right, we already found that over here. So we have our left endpoint. Copy that. Oops, I meant to put it here. Let's do that again. So my summary statistics, I'm going to copy this. 2.66765. Okay, didn't seem to like that, so we'll just write it in. So we got 2.66765, our left endpoint. And then the right endpoint was 3.18839. So 3.18839. Okay, so this is the confidence interval, 2.66765 to 3.18839. Now, to interpret the confidence interval, we're simply going to write a sentence that looks like this. We are 95% confident. Notice how we put our confidence level right in there. That the population mean weight of Canadian pennies is between the 2.66765 and 3.18839 grams. Okay, So this is the interpretation. The interpretation is a sentence, okay, that explains what those numbers are. So we had a left endpoint, 2.666765, a right endpoint, 3.18839, and these then mark the endpoints for the confidence interval estimate of the population mean. Now we did a 95% confidence interval, so that tells us how confident we are. It's like the probability. There's a 95% chance that the true population mean, nope, let's back up there. Oops. Okay, sorry, we're having trouble seeing this. I want us to be able to see this while I explain it. Okay, so we're 95% confident that the population mean weight of pennies is between 2.66765 and 3.18839 grams. That means there's a 95% chance that the real population mean is somewhere between those two values. That 5% then that's left over, that 5% is a probability that we actually got an unusual data set and we are off, so that there's a 5% chance that we're wrong and the population mean is not contained in that interval. So this is how we answer the question, how good is the point estimate? We had a point estimate of 2.92802 grams. Now we have a margin of error, though, of 0.260374 grams. So it's like saying, okay, we're estimating the mean weight of pennies as 2.92802 grams, give or take 0.260374 grams. All right, so that puts us between 2.66765 grams and 3.18839 grams. Well, how certain is that? Well, there's a 95% chance that the true mean is within those two values. All right, and there's a 5% chance that we're wrong and we didn't estimate it correctly. Now we can use this mean to either support or not support certain assertions. So notice here the question in part E, according to this confidence interval, could the population mean weight of Canadian pennies be 3 grams? Well, all we have to do is look at our interval and see, does that interval contain 3 grams? It's 3 in between 2.66765 and 3.18839, and we see yes, indeed it is. So the answer is yes, since the interval contains 3 grams. All right, so since the interval contains 3 grams, it's quite possible then that the actual mean weight, the population mean weight of pennies is indeed 3 grams. Now, there's another question down here that would relate to if you wanted to go further, perhaps, and gather another sample of pennies with a tighter margin of error. Notice here, what sample size would you need if you wanted to construct a 95% confidence interval with a margin of error of 0.1 grams? See that our margin of error for the problem we did, we got a 0.26 grams margin of error. What if we want our margin of error to be only 0.1 grams? Well, then how many Canadian pennies should we sample? That is something that we can easily find out by using a formula, and we'll address that later. Let's instead look at another example. So in this example here, we have the volumes of 24 cans of Pepsi, and those are all listed here in column A. Now, recall that a can of soda is always labeled as 12 fluid ounces. So here are volume and fluid ounces. They're all 12s, but they're actually a little bit more than 12. All right? Actually a little bit more than 12. Notice nothing there is actually less than 12.2. It looks like 12.3, 12.2, 12.3, 12.4 grams are the weights we're getting. I mean fluid ounces. All right? So we want to find again the point estimates of the mean and standard deviation for this data set. Recall that the standard deviation is a measure of variation, and remember we use that standard deviation in order to find a standard error, which is then used to find the margin of error. although that is done for us using the summary statistics. So an example again, just using Excel, we'll go to Data, Analysis, Descriptive Statistics, where we need to highlight our input. I make sure that it knows we have labels in the first row, and then I'm going to have this put in a new worksheet that'll label some stats too. Summary statistics, confidence level again, 95%. Click OK. So here we are, some stats 2. Volume is fluid ounces. And here is our sample mean. 12.27083. Now, our data was only to 1 decimal place, so we really can't round this off to more than 2 decimal places, or we imply there's more precision in the measurement than is actually called for. So there's the mean of 12.27, and then here's our confidence, 95% confidence level, margin of error of 0.3609. So again, remember, this is the margin of error. So we can find then a confidence interval so that the left endpoint is just the sample mean minus the margin of error. Alright, and actually let's cut that down to just the 2 decimal places as well. And then our right endpoint is the sample mean, is the sample mean plus the margin of error. Okay, so we see then our confidence interval, all right, between 12.23 fluid ounces and 12.31 fluid ounces. All right, that's our answer for the confidence interval. Now for our point estimates, we already had the mean of 12.27, and here's the standard deviation. Again, let's cut this down to just the 2 decimal places. All right, so to answer exercise 2, our sample mean, x bar, is 12.27. Our sample standard deviation, S, is 0.09. Our margin of error, E, is 0.04. And our confidence interval is 12.23 to 12.31. All right, and this is in fluid ounces. So now we can interpret this confidence interval. We are 95% confident that the population mean volume of cans of Pepsi is between 12.23 and 12.31 fluid ounces. Okay, all right. Okay, so that means there's a 95% chance that the population mean volume of cans is between 12.23 and 12.31 fluid ounces. 5% chance that we're wrong. We just got a funky data set. Now the question here, does the confidence interval support the assertion that the population mean volume of cans is 12.2 fluid ounces? Right? Well, does our interval contain 12.2 fluid ounces? No. All the values of the interval are greater than 12.2. So the answer here is no. All values are in the interval are greater than 12.2 fluid ounces. Actually, what we can say is that the confidence interval supports that the population mean volume of cans of Pepsi is actually greater than 12.2 fluid ounces. So not only is the population mean volume of Pepsi greater than the 12 ounces labeled on the can, we're 95% confident that it's actually greater than 12.2 fluid ounces, because it's 95% chance it's between 12.23 and 12.31. All right. Here, let's do one more example. All right. Nicotine content of 29 brands of cigarettes are listed here. Okay, so here's our nicotine content. Again, we want to find a confidence interval, but starting with the point estimates of the mean and standard deviation. So we go to data, data analysis, descriptive statistics. My input, A1 to A25. No, I want to go further. Okay, oops, let's do that again. So let's get all my data here. Let's delete that. So highlight all my data from A1 all the way to A30. Labels, new worksheet, I'm going to call it SumStat 3. Summary statistics, confidence level 95. Okay, here are the statistics for the nicotine content. Here is the sample mean. Here is the sample standard deviation. Here is the margin of error. Our data set only had 1 decimal place, so these values should only be to 2 decimal places. So let's take these down to 2 decimal places. Alright, so we see then that the sample mean nicotine content is 0.94. So the mean x bar is 0.94. The standard deviation S is 0.31. The margin of error E is 0.12. So we can find our confidence interval. So let's go back to some stats. Left endpoint of the confidence interval is the mean minus the margin of error. Let's remind ourselves this is the margin of error. And the right endpoint is the mean plus the margin of error. So we see then that the 95% confidence interval is between 0.82 and 1.06. So let us go back to exercise 3. 0.82 to 1.06. Whoops. 0.82 to 1.06. Yeah, 0.82 to 1.06. We don't want that here. Alright, so here then is the confidence interval. Interpret it. We are 95% confident that the population proportion of population mean okay, we're 95% confident that the population mean nicotine content of cigarettes is between 0.82 and 1.06. I don't even know what the units are, so I guess that's it. So we're 95% confident that the population mean nicotine content of cigarettes is between 0.82 and 1.06. Okay. Does the confidence interval support the assertion that the population mean? The rest of the question is missing. So let's make one up. Does the confidence interval support the assertion that the population mean nicotine content of cigarettes is less than 1, whatever units that's in? Well, let's see. We're 95% confident it's between 0.82 and 1.06. Oh, look. It can be a little bit bigger than 1. So less than 1? Not necessarily. It's possible it could be as much as 1.06. So the answer is no. Some of the values in the interval are greater than 1. Okay? So if we were to support the claim that the content was less than 1, every single value in this interval would have to be less than 1. But we can see that some values are greater than 1, so that's not true. Now, if the claim had just been equal to 1, we would have been able to say yes, because 1 is in the interval. So there's a difference between equal to 1, in which case 1 just has to be in the interval, and less than 1, in which everything has to be less than it. So if we go back to exercise 1, remember the claim was, could it be 3? And we said, yes, it could be 3, because 3 is contained in the interval. If it had said more than 3, we would say not necessarily, because there are some in here that are less than 3. In exercise 2, we said, did it assert that it is 12.2? We said no, not in there, but we could assert greater than 12.2 because everything in here was greater than 12.2. So for this one, does it support the assertion less than 1? No, because some values are bigger than 1. Okay? All right. So let's talk, before we get to sample size questions, let's talk a little bit more about the relationships between, let's actually go to a summary set. Let's look a little bit more at the relationships between the, let's see, the standard error, the standard deviation, okay, count, and the margin of error. All right, so the standard error, whoops, this is wrong, is the standard deviation divided by the square root of n. Okay, so the standard deviation divided by the square root of n is a definition of the standard error. Okay, it's a definition of the standard error. All right, so what does that mean? Standard error. Well, standard error has to do with the sampling distribution of means. All right, and why it's related to the standard deviation. So let's go over here and let's talk about the sampling distribution of means. Now, the sampling distribution of means is explained in a theorem called the central limit theorem, and the central limit theorem is extremely important in statistics. It's what allowed us to do everything that we just did in those exercises so that we could get that interval estimate. What the central limit theorem says is if you randomly select samples of size n from a population with some given mean and standard deviation, doesn't matter what the population looks like or what the mean and standard deviation are in general, but if you randomly select samples of size n and compute the sample means from these samples, right? Compute the sample means, and then let's say you constructed a frequency table and histogram, the distribution of the sample means would be approximately normal. It would be bill-shaped, right? And the center of this distribution would be equal to the population mean of the original population mean, and the standard deviation of this distribution, which is called the standard error, would actually be smaller than the original standard deviation of the population. And it would be smaller by a square root of n. Okay? It would be smaller by a factor of 1 over the square root of n. So you would divide the standard deviation by the square root of n to get a smaller standard deviation. All right? Now, this is true. It's close to the mean. Okay? Every time you take a sample mean, we're assuming that the sample mean is close to the true mean. So if all the sample means, okay, are decent, they should be close to the true mean. They all should be hovering or centered about the true mean. That means that the sample mean is unbiased. And if they're all hovering about the true mean, then that means the middle of the curve should be the true mean. Also, we want to make sure that our sample means are all close together. Not only are they all huddled around the true mean, but they're all close together and huddled around the true mean. So what we end up with is a bell-shaped curve where most of the data value is in the middle by the mean. So that's what gives us a bell-shaped curve where the middle of it is the true mean and most of the data is in the middle, because then by being close together our data values are consistent. By being close to the true mean, the sample means are unbiased. So the sample mean is an unbiased, consistent estimator of the population mean. So the central limit theorem says then that we basically have a bell-shaped curve where the middle is the real population mean. And then the variation in the distribution, which we now call the standard error as opposed to standard deviation, to differentiate it from just a distribution of values versus a distribution of sampling means, the standard error will be smaller than the standard deviation of the original population, because if everything should be consistent, hovering around the true mean, you're going to expect less variation. And how much less variation you have actually depends on the sample size. So the bigger your sample, the smaller the standard error. That's why we're dividing by the square root of n, right? The bigger the sample size, the smaller the variation. The less variation, the smaller the standard error. So remember then that larger samples have less variation, smaller samples have more variation. Okay, that's really important. I will actually write this down here, that larger samples have less variation, whereas smaller samples have more variation. And this is extremely important and something you never want to forget. Lots of things we do is based upon this, and this affects the margin of error, right? So the sample size will affect the margin of error, and it does so by affecting what we call the T-score. Because what is this T-score? Okay, well, we said that the distribution of means is approximately normal. All right, it's approximately normal. Now, the larger the sample size, the closer to normal. So let me make note here. Larger the sample, I'm going to say larger the n, larger n, closer to normal. All right, so the larger the sample size n, the closer to the actual normal distribution, which remember follows a specific formula. All right, now if it's actually not normal, doesn't follow that formula for the normal distribution exactly, it can be approximated, right? It's approximately normal, and we approximate that, right? It's approximated with, oops, I have that down here. It's approximated with something called the student's t-distribution. Now, the student's t-distribution is a bell-shaped curve, and the middle of the curve is going to be the population mean. But now this has more variation in it due to smaller samples. This basically takes into account the sample size so that the larger the sample size, the closer to a normal distribution. The smaller the sample size, the more variation from a normal distribution. All right. Now, remember that the margin of error is a maximum likely error. Maybe, I didn't mention that today. But let me write here that the margin of error is the maximum likely error between the sample mean and the population mean. Okay, so the margin of error is defined as a maximum likely error between the population mean and the sample mean. That's basically going to be the width for the middle part, right? You have a bell curve, right? So you have a nice bell curve, and the middle are the likely values because that's where most of the means are, and then you have some unlikely values on the ends. So that middle part is a likely value, and that likely value is determined by the confidence level. So the confidence level defines the likely values, and these are the likely middle values of the bell curve. All right. So remember that most data within a normal distribution is about 2 standard deviations from that middle. So if we actually know the number of standard deviations from the middle, that defines likely. So it's going to be about 2. All right, but now we're looking at a approximation of the normal curve, so it won't be exactly 2. When we were with the normal distribution, it was actually a little less than 2. It was 1.96. Okay, so when you're working with the normal distribution, it's 1.96 standard deviations from the middle. But if you have smaller sample sizes, then the number of standard deviations from the mean, instead of a z-score of 1.96, it'll be a t-score. It'll be a little bit more than 1.96, but it'll still be around 2. It'll still be around 2. So what we're looking for is a number that's approximately 2, probably a little bigger than 2, all right? And that will be the number of standard deviations from the mean. And that margin of error will be that maximum likely error between the sample mean and the population mean. So basically means the distance from the middle of the curve up and to a tail, where the tail then defines the unlikely values. So we have to use a student t-distribution to find that t-score, because that will tell us the number of standard deviations from the mean. And so to do that, we have to use what's either some kind of t-inverse command. And in Excel 2007, t-inv is the inverse command. Excel 2010 will use t-inverse 2t, because remember, when you're working with a normal distribution, you have 2 tails of unlikely values, those too small and those too big. It's the middle 95% that's likely. So we have 2 tails defining the unlikely. Now, the student t-distribution completely depends upon different sample sizes. The sample size, because the bigger the sample size, the closer to the normal. So what we have to do is basically tell the t-inverse command how big our sample size was. But instead of entering the sample size, we work with degrees of freedom, okay? And degrees of freedom is 1 smaller than the sample size. All right, so remember over here in the overview, we said the t-score depended upon degrees of freedom, which is 1 less than the sample size. The t-score also depends on a probability, and the probability is 1 minus a confidence level, so 1 minus 0.95 or 0.05. We're going to use t-inverse or t-inverse 2 tail to do that, and I'm going to give you some examples then on how that works. So if we go over here to the summary stats for the weights of the Canadian pennies, a t-score, okay, so I'm just going to put it in here. A t-score is a number of standard deviations from the mean. So what we have to do then is we have to find out, all right, how the number of standard deviations from the mean based on a given confidence level. So to get this t-score, we have to go to the formulas, the math function, statistical, and looking for t-inverse. Now I have Excel 2010, so I'm going to use t-inverse 2t. So here's t-inverse 2t, right? And notice there's the probability. That wants the probability in the tails, the unlikely probability. And we're defining unlikely as 5% here. Degrees of freedom, 1 less than the sample size. Remember, our sample size was 10 here, so 1 less than 10 is 9. And look at that. I said a little bit more than 2. Right? So here it is, about 2.262. Right? So this is the t-score. Okay? Now, the margin of error then is actually defined as the t-score times the standard error. Right? The t-score times the standard error. So here we're going to have our t-score, which is the number of standard deviations from the mean, and the standard deviation for a sampling distribution of means is the standard error. So we're going to multiply that by the standard error, and look at that. There's that 0.260374. Okay, So that is how Excel computes the margin of error. All right? It knows the count. One less than the count and the given confidence level here. Remember, we had to pick 95%. And it then finds the t-score, and then it multiplies that t-score by the standard error. Okay? And that gives the margin of error. All right. Now, remember, the standard error is the standard deviation of the sampling distribution of means. And the standard error is going to be smaller than the standard deviation of the population of weights. And that was why here, this is the standard deviation for the weights of pennies, right? This is the mean for the weights of pennies. So the standard error is a measure of variation for a distribution of sample means, and that distribution of sample means is going to be smaller than the variation in just means of all the pennies. So we take that standard deviation, divide it by the square root of n. Remember, n is the sample size, and that will give a smaller value. So notice the standard error is 0.115, whereas the standard deviation was 0.364 rounded off. All right, so we can see it's significantly smaller, 0.115 versus 0.364. All right, and so we want the variation in the sampling distribution, and that's why we multiply the t-score by the standard error to get the margin of error, and then the margin of error is added and subtracted to the sample mean to get the confidence interval. So that is the relationship between all these things. Let's look at the relationship again for the other examples. So remember, in exercise 2, we were looking at the volumes of Pepsi cans, right? Which is labeled as 12, and it looks like it's actually more like greater than 12.2. I mean, it's between 12.23 and 12.31, right? Margin of error 0.04. So when we computed these point estimates, this is the average volume from our sample, and this is the measure of variation in our sample. So the average volume is 12.27 fluid ounces, all right, with a margin of error of 0.09. I'm sorry, with a standard deviation of 0.09. That's a measure of variation. When we do the margin of error, we basically want to measure a variation, okay, for the sample means. This is a measure of variation just for individual pennies. This is a measure of variation for means, how much the different means could vary from each other, all right? And so the means, how much? Well, the mean could be 12.27, give or take 0.04 fluid ounces, and that's how we got this confidence level. So let's go back and look at the summary statistics here. All right, so the standard deviation of the original population is estimated to be 0.09. The standard error is how much a distribution of sample means varies, right? So remember, this 0.09 is how much the individual weights varied. This 0.0175 is how much the mean weights vary. And it is found by taking the standard deviation and dividing that by the square root of the sample size. All right, so remember, smaller sample sizes, more variation. Bigger sample sizes, less variation, right? And so here's that standard error. It's smaller than the standard deviation based on how large the sample size is. Okay, now for the margin of error, we have to define what is considered likely, and we're defining the middle 95% as likely. Therefore, the 5% divided into the tails is unlikely. T-score defines the middle likely. So we have to find out what value separates the middle 95% from the unlikely 5%. So if we just focus, say, on the middle 95% from the top 2.5%, we go to formulas, more statistical, T inverse. We're looking for a bell-shaped curve that's approximately normal, which is approximated by the student T, two-tailed because we're going to have our unlikely 5% distributed evenly in the two tails. Degrees of freedom, one less than sample size, 23. Lowest, again, it's around 2, but this time it's a little closer to 2 than in the previous example where we had a smaller sample, right? So here, the t-score is 2.068, just a little bit more than 2 standard deviations from the mean when we had a sample size of 24. Recall that when our sample size was only 10, all right, we were 2.26 standard deviations away from the mean. So by increasing our sample size to 24, we've decreased the t-score. Okay, it's a little closer to the middle, 2.06, a little smaller. We take this t-score, and to get the margin of error, we're going to take the number of standard errors, which is like the standard deviation of the distribution of sample means. We'll take the number of standard errors from the mean, multiply that by the actual value of the standard error, and that gives us the margin of error, because remember this was rounded off. This gives us the margin of error, and that then tells us how much the sample means would vary. All right? So we have a mean volume of 12.27 fluid ounces, okay, give or take 4 fluid ounces, and this is an estimate of the average weight, all right? So if we took a bunch of averages, it should average, it's going to be about the real population mean will be within 0.04 fluid ounces of 12.27 fluid ounces. So we're 95% confident that if we randomly select a sample of size 24, we are 95% confident that the population mean volume is in between 12.23 and 12.31. So it looks like it's bigger than 12.2. All right, so notice the margin of error got a little bit smaller when we had, see here, the margin of error, or I should say the t-score, okay, got a little bit smaller when we had a bigger sample. Okay, now we had one more, right? We had this exercise 3, and here we had 29 rather than 24. 29 cigarettes. Let's see how that affected things. So what we found then is that the average nicotine content was 0.94, all right? We had a standard deviation of 0.31, okay? So any particular cigarette, okay, will have a nicotine content of 0.94, give or take 0.31, all right? But on average, the average nicotine content of a bunch of cigarettes, right? The average nicotine content is 0.94, give or take 0.12. All right, and this standard error then is the distribution of sample means. So the standard error is a distribution of sample means which is smaller than just the distribution of individual nicotine amounts. We divide that by the square root of the sample size. All right, and so we see that the variation in sample means is about 0.058, which is a lot smaller than the variation of the nicotine content of individual cigarettes. So individual nicotine content varies more than the average nicotine content. All right. Now, we're defining 95% as likely, so 5% unlikely. So the t-score is going to be approximately 2, but it's going to be a little bit closer than 2 even from the last one. So notice when we had a sample size of 24, we had a t-score of about 2.068. We're increasing that, but just a tad. It's now 29, so let's see what the t-score here is. So we go to formulas, more functions, statistical, t inverse 2t, 5% we're defining as unlikely distributed evenly into the two tails. This time our sample size is 29, so the margin of error is 28. Notice instead of 2.068 we have 2.048. See, the t-score got even smaller. Okay, so that's even closer to the middle. But now to find that actual distance in whatever the same units are here, right, to put it in the same units as this, that's when we have to take then the distance from the mean times, right, or the number of standard errors from the mean times the actual value of the standard error, and that gives us a physical distance. Okay, and we had rounded that down to the 0.12. Okay, so then this gave us our confidence interval for the mean. Hope I didn't go through that too quickly, but I wanted to give you lots of examples, or at least, the 3 examples, so we can see the difference between how much just the individual nicotine contents could vary versus how much the average of nicotine contents could vary, and then how that helps us find that maximum likely distance. All right, so the difference between the standard error and the standard deviation is the standard deviation is a variation for individual nicotine content of cigarettes, or individual cigarette nicotine content, whereas the standard error is a variation for average nicotine content of cigarettes. Okay, right, so the variation for the average nicotine content versus a variation for individual nicotine content. Okay, and average variations, the variation for the averages is smaller. How much smaller depends directly on the sample size. So the bigger the sample size, the closer to 2 the t-score, the smaller the t-score. But then that's just the number of standard errors. We actually want to know the number of units, right? We want to know how far from the mean given the same units as the mean, and that's why then we have to multiply that t-score by the standard error. All right, so that concludes this video presentation, and then I'm going to have another video presentation that discusses the sample sizes by themselves, meaning, all right, now we've already gotten some data. I want to have a smaller margin of error than this data gave me. How many should I sample so I can get the smaller margin of error?